All right. So now that we have talked about Kirchhoff's rules and the series and parallel rules, that just leaves us with solving circuits that aren't entirely made up of series resistors or parallel resistors. So now we're going to mix and match. So we said that if you have two resistors in series, you can find their equivalent resistance by just adding the resistors. But in parallel, we have this rule that we've been calling the reciprocal rule to find the equivalent resistance. And again, what we mean by equivalent resistance is this would be a concept of a fake resistor that mathematically makes the circuit obey Ohm's law. So we create this concept of Req because it allows us to solve for the total current in a circuit, even when it's very complicated. So this is a mathematical construct, but it does give us the correct answer, and it will correctly model the behavior of the circuit as a whole. So how it will work is we're going to start combining all these resistors to make Req, and then we'll break Req back apart when we want to analyze it. So first, we're going to prove these rules. We actually didn't do that yet. So now that we have Kirchhoff's rules, that being the loop rule and the junction rule, we can now actually derive these results for Req. Now, it probably doesn't take much convincing that the series equivalent resistance is just the sum. Right? If I have to stop for a time R1 at the first traffic light and I have to stop a time R2 at the second light, it's going to take me R1 plus R2 time in total. But it's nice to actually prove it. So Req, by definition, is equal to the battery voltage divided by the total current in the circuit. And to make this work, we need to get a whole bunch of cancellations to happen, and we have to use Ohm's law in the circuit. So to do that, we have to think, I want to write all of these circuit quantities in terms of something that is shared by everybody. And since this is a series circuit, we know that this is the same I. So if I can write everything in this circuit in terms of the current I can get some cancellations. So here, we first apply Kirchhoff's loop rule. Because Kirchhoff's loop rule says that my battery EMF, the amount of potential I gain by being stepped up, must be dropped in total by the two resistors together. So I can actually write the battery EMF as the two drops, because the two voltage drops must equal the battery voltage. And what is delta V? We know what delta V is. Delta V is IR. And since everybody has the same I in series, notice what happens. Everybody brought a current. Cancel, cancel, cancel. So we're just left with, look at that, Req is R1 plus R2 in series. So series had the same current. So we wrote everything in terms of currents and applied the loop rule. So you can guess that in parallel, every single thing is going to flip-flop. So now everybody is going to have the same delta V. So we're going to expand everything in terms of the battery voltage and use the junction rule. Because if we give ourselves a little junction here, this would be our total current. We know that some of it is going to go down the R1 path, and some of it is going to go down the R2 path. So, same idea. Req is the battery EMF divided by the total current. And I actually don't want to eliminate the battery EMF this time because everybody shares that. That's the voltage drop across both resistors, and it's the battery voltage. So this is going to be our shared constant. But this time, I want to write the total current in the circuit because the current gets split into I1 and I2. And you can see where we're going here because Ohm's law says that current is delta V over R. So we can just replace I1 with epsilon over R1. We can replace I2 with epsilon over R2. Our common factor of the battery voltage cancels out, as it should, and we get 1 divided by 1 over R1 plus 1 over R2. And that's really cumbersome to write. That is the correct expression, but just to save space, remember, if you're dividing by something, that's the same as giving it a -1 exponent. So there we go. Our parallel is given by the reciprocal rule, just like we thought it should. So now we've proven those facts. So to find the equivalent resistance of a general circuit, combine resistors that are only directly in series or parallel each time, redraw the circuit as needed, and continue the process until you get one resistor. This is Req. So the rules for resistor combining is you can only combine resistors that are directly in series or parallel. And you just keep breaking down and breaking down and breaking down, and you can get to one resistor. Usually. Now there's weird scenarios where you can't do this, but 90% of the time in this class you can. If not, the like classic example of one you can't do would be like a diamond shape of 5 resistors. Okay, let's do it. So first, we're going to do our first scan, and we're only going to combine resistors that are directly in series or parallel. Well, these are clearly series. That makes 8R. These are parallel. So you might want to check what that is. Last time I said this was one that will do enough that you might just kind of remember. It's actually 2R, but if you actually do it, this would be the relevant fact for you. Okay, so I feel like that's enough. Like, you can definitely do more than this at once, but just keep redrawing it. You'll mess up a lot less. So we have turned the top branch into an 8R. We did nothing to the middle branch, who is also 8R. And then the bottom, we turned that parallel into a 2R. So we get a 4R and a 2R. So now we can see another quick combination before we finish. We see that the 2 and the 4 make a 6. So now we can just redraw. So we get an 8, an 8, and a 6. All right, so now we got to do parallel. So we are going to deal with some fractions. It's just a part of life. So Req is going to be 1 over 8 plus 1 over 8 plus 1 over 6 to the -1 times R. So we're just going to simplify what that is. So 1/8 and 1/8 is 1/4. 1/4 and 1/6. Their common denominator would be 12. So 1/4 is 3/12. 1/6 is 2/12. So I would get 5/12 to the -1 power times R. So that makes 12/5 R. So kind of the gross equivalent resistance. But that's always nice to practice our arithmetic skills. So again, we combined the parallel and series first, and then we just kept breaking it down, breaking it down, breaking it down until we're left with a single resistor. Here's an interesting one. A student correctly computes the equivalent resistance of a circuit in ohms using their calculator and they type in this expression. So with one single line, they calculated REQ using this. So let's try to figure out what the circuit is. So here's what I notice. First of all, what I notice is that I have something plus something plus something. So this tells me there's going to be 3 chunks to this circuit in series. There's a 1, a 2, and whatever the hell's going on inside that thing. So that means that our circuit diagram is going to look like 1 ohm, 2 ohms, and something. So we don't actually know what's going on inside here yet. But we do know that whatever it is has a resistance equal to this. So let's try to figure out what's going on there. So the double fraction, the compound fraction here is kind of weird. So let's try to break that down. So this is what it looks like. So this is what it looks like. So what this looks like is, we said a nice trick to make this easier to look at would be to just make this a negative exponent so we don't have to read the compound fraction. So you might like to read this better as 1 over 3 plus 1 over 4 plus 5 plus 6 to the negative 1. And now that's actually a lot clearer to me what's happening, because now I see that we have this entire object is actually just a 1 over 3 in parallel with a 1 over 4 plus 5 plus 6. So this means that this black box that we originally knew nothing about is actually just 2 parallel branches. So we can draw our circuit as 1 ohm, 2 ohm, and then it actually says we can break this off into 2 parallel branches. So one of the parallel branches, that's really easy. That's just going to be 3 ohms. But what about the other branch? Well, the denominator here says it's a 4, a 5, and a 6 added together. So that's actually just series. So my second branch here is actually just a 4, a 5, and a 6. All in series. So that's actually a circuit diagram consistent with this. And we can check that this makes sense, that this is a valid solution. So this is what we came up with. So what would REQ be? Well, REQ would be equal to 1 ohm plus 2 ohms plus whatever this parallel resistance is, which would be 1 over 3 plus 1 over 4 plus 5 plus 6 is the equivalent resistance of that branch to the negative 1. So it does end up working. And notice that is exactly what this expression is. So it works. Obviously not the only solution, but this is probably the simplest one to kind of look at. All right, now we have a very scary looking circuit. In the circuit shown below, calculate the total power dissipated by the resistor network. Well, first, that looks awful. That looks absolutely awful. Total power dissipated. Power is IV, so I have to do IV, 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 IV 12 times? Absolutely not. So another powerful, oh, that was kind of a pun. Well, a powerful thing with REQ is that you can use it to find totals. So anything about your circuit you want that involves a total, REQ is great for. So we can actually write that the total power in our circuit would be equal to I total times delta V total, which would be equal to the battery current times the battery voltage, epsilon. But remember, there's also two more power formulas that we can get with Ohm's law. So if we wanted a different power formula, we could actually write this as the battery current squared times the total resistance. So if we're doing the total, that's going to be Req. Or we could use the not centripetal acceleration version of the total battery voltage divided by Req. And usually if we want total power, it's this centripetal one that we like, because you don't know anything about current. So if you had to calculate current, that's sort of an extra step. So notice we already have the battery voltage, that's 60 volts. So that means all we need is actually to find Req for this circuit, which that's easier said than done because this is slightly scary looking. All right, so again, we can only combine directly in series or parallel first. So easy. 2 and 4 makes 6. Easy. 6 and 4 makes 10. All right, now what? Well, these are also in parallel. So these three are in parallel. So there's kind of an interesting trick with parallel circuits that I haven't talked about yet. And it's pretty easy to prove from the rule. If you add a bunch of identical resistors in parallel, the resistance becomes divided by the number of resistors that there are. So if I had a 50 into 50 in parallel, I'd get 25. If I had 10 ohm resistors in parallel, I'd get 1 ohm. So since I have 3 identical resistors in parallel, this actually works out to 25 ohms. The more common one you'll see is if you have 2 identical resistors in parallel, Req is half. Of course, just work it out, right? This is just 1 over 75 plus 1 over 75 plus 1 over 75, raise it to the -1 power. It's pretty easy to see why this works. So that becomes 25. And then what about this? Well, over here, notice that this is actually a sneaky parallel. This is a sneaky parallel because I can start at this point and get to this point by going through the 100 ohm this way or the 100 ohm this way. And since I get to that spot by going through exactly one of the two 100 ohm resistors, this is actually in parallel. And this is more clear if you color code it. I just don't have that many colors. And this also uses the little parallel corollary that 2 identical resistors in parallel results in half the resistance. All right. That was a significant amount of progress. So we actually made this a lot more manageable now. Because if we go here, now our circuit will look like now our circuit is going to look like this. We're at a 15 and a 25. And then we have a 50 and a 10. So that looks a lot more manageable. Oh, and I should make this so it doesn't get cut off. That would be great. Okay, so now we can do a little bit more combining because we can see that we're going to get, you're still 60 volts. You're still 6 ohms. You would be 40 ohms. And you would be 60 ohms. And then we can combine those. We can combine those in parallel. So if we do that, once again, I got our 60 volts, 6 ohm, and then what is 20, what is that? What is 60 and 40 in parallel? Well, we have to work that out. it would be 1 over 60 plus 1 over 40. To the negative 1. And this is not one that I would have guessed. It's actually 24 ohms, if we work that out. So this means our Req is just going to be 30 ohms. And that's actually not what we were asked. We were asked for the total power. So we can find the total power by doing the battery EMF squared, and then we divide by Req, which is 30 ohms. And if we do that, we're going to get 3600 divided by 30. 3600 divided by 30, which would be 120 watts. So pretty significant power output right there. So notice that even though this was an absolutely insane circuit, when we took it step by step, we could reduce, 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 and get it down to something manageable. Now, it was a lot of steps, right? It was totally a lot of steps. But just follow the process. And all the numbers worked out nice along the way. So shout outs to me for that. All right, now we have a nice little ranking task. In the circuit shown below, all resistors and batteries are identical. So we have battery A, which is a series. We have battery B, which is a parallel. And battery C, which is a combination. Rank the power output of each battery from least to greatest. Justify your ranking qualitatively. Okay, well, what is power? Power is I delta V. So power is I delta V. It's the rate at which charge is being, or energy is being transferred. So since the voltages are the same, we know that power is equal to I delta V, which is equal to the total current in the circuit times the battery voltage. Well, the battery voltage is fixed. So this means that we're really just ranking I total. So we're looking at where is the current the greatest, where is the current in the middle, and where's the current the least. So we can actually make the argument that battery A, this is a series. Battery A is series. This is a series circuit. So it has the highest Req possible with 3 resistors because it's just addition. So this would be the lowest current. So we get the lowest power from battery A because we have the least current. And conversely, battery B, we said that the parallel rule reduces resistance. So if you have 3 resistors in parallel, you've opened up a bunch of extra paths that your battery needs to supply current for. So this is parallel. And parallel has the lowest Req possible. And if it's the lowest Req possible, that means it's the highest I total. And for a similar argument, battery C, the resistors aren't all in series, nor are they all in parallel. So we know that this is going to be an intermediate Req, because this is a combination circuit. So we actually are able to rank the current and therefore the power output without actually doing Req, because we know that series is addition, parallel is going to be some sort of resistance reduction. It's actually division in this case. And combination is a mix. So we actually know that the least power is A, the most power is B, and C is in the middle, and they don't tie. Since all the batteries have the same voltage, the battery that outputs the most current will supply the most power. Thus, we're just ranking, sort of doing an inverse ranking of REQs. And since REQ is highest in series and lowest in parallel, the series has the least power, the parallel has the most, and the combo is in the middle. Let's do the power outputs. So the easiest way to find the power output would be that the power from the battery, yes, it's equal to I total of the battery times the battery EMF. But since we don't know the current in the circuit, it's easiest just to use this power expression that we used last time. So we know it's just going to look something like this for each battery, where the power output from A is going to be epsilon squared over REQ, and we'll just do the shameless copy paste 3 times, and we're going to go back up and calculate our REQs. All right, well, we're given that all these resistances are R. So it's pretty clear that battery A's REQ is going to be 3R. R plus R plus R. What about parallel? Well, we can use the parallel corollary from the last problem that says that if you're adding a bunch of identical resistors in parallel, it turns to division. And I think it might be useful just to show you here, because if we have 1 over 1 plus 1 over 1 plus 1 over 1 all to the -1, that would be equal to 1/3 times R for this circuit. Because if we have 1 over R, 1 over R, 1 over R, we'd get 3 over R, and we add the reciprocals, and then we got to flip it. So REQ is 3R for the series, it's 1/3 for the parallel, and then what about the combo? Well, same idea, except we'll just use that parallel corollary again. This would be 1 over 1 plus 1 over 1 to the -1, which is equal to 1/2 R. But that's not the circuit REQ. That's actually just the REQ of the parallel combination. So then we can tack on our extra R resistance right here, and we get REQ is 1 plus 1/2, which is 3/2 R. So now we can go ahead and plug in. So the series REQ was 3R. So our power output is 1/3 with appropriate units. Our parallel was 1/3 for our REQ. So we actually get 3 times epsilon squared over R for this parallel case. And then for the combination case, our REQ was 3/2 R. So we get 2/3 as our multiplier. So notice, if we look at our power rankings, we have 1/3 as the lowest, 2/3 is our intermediate, and then 3 is the highest for our factors in front. So we do get, as expected, series was the least power and parallel was the most. So now we'll actually solve a combination circuit. And when we mean solving a combination circuit, that of course means like literally finding everything we could want. So to solve a combination circuit, we typically break everybody down to find REQ. Then we find the total current. So the key to these combo circuits is find I total. Because if you find I total, you can find the voltage drop across anything that is in series with the battery. And then you just start doing loop rule and junction rule to fill in the gaps. There are cases where this is not enough and you can't just REQ things, but we'll talk about that. In most cases, you can combine them. So this is a typical combination circuit that we'd see. So the goal would be you'd combine these, then you'd combine it with this, and then you get I total. I total hits R1, you find the drop across R1, and then loop rule helps you work out what all the other drops have to be. So let's do it. All right, new circuit dropped, but old techniques, right? You know I'm going to color code it. You know I love my color-coded potential diagrams. So we know that you are at a height of 0 volts. You are going to be stepped up by 30 volts, so your height is 30. And that leaves some intermediate potential that is to be determined. Okay, so it always says our first step should be finding Req. So let's do that. That is usually a good first step. So Req. So we know we want to find Req. So first, notice I have my 12 and 24. Those are in parallel. So I can directly combine 1 over 12 and 1 over 24 in parallel to get whatever that parallel branch is. Let's see. Is this a cousin of the 3 and the 6? I think we're about to find out. I'm going to guess that this is 8. This is 8 ohms. Still not Req, right? Because all that did is that just condensed my circuit into this object right here. And now, of course, we can just solve, because now we have a series, so this is just going to become 10 ohms for Req. All right. So now what we want is I total. So the whole reason we do Req is not because we love the equivalent resistance. It unlocks the battery current. The whole reason to do Req is because the total battery current is the battery voltage divided by Req. Battery voltage was 30 volts. Req was 10 ohms. So we get 3 amps as our battery current. Okay, not particularly helpful on its own, but we'll see why. So we just found some things out. So we can actually fill out the battery column or the battery row in our table now, because the equivalent resistance of our circuit we solved to be 10 ohms. The battery voltage was 30 volts. The battery current was 3 amps. Then the battery power input, we have the formula power equals I delta V, or pick the other two, I really don't care. All of them will work. Is, let's see, I delta V. I delta V 90. 90 joules per coulomb times coulombs per second equals 90 joules per second, which is a watt. So all of our resistor powers better add to this, or else we had some problems, because we said that the total energy dissipated by the resistors is just the battery power. Okay, why do we care? So the battery current is 3 amps. So what this means is that the battery is pumping out 3 amps of current. And that's super helpful to us, actually, because we actually have a resistor that's getting hit by the 3 amps. It's this 2 ohm resistance right here. So we can just do Ohm's law, because our current through the 2 ohm resistor is 3 amps. And since we know Ohm's law just says delta V equals IR, or I equals delta V over R, depending on which one you'd like, we can see that I times R would be 3 times 2, which is 6 volts. And I delta V, 6 times 3 would be 18. Okay, so that's helpful because now we've unlocked something else. So this is just a chain of unlocking more and more information about the circuit. So now we know this voltage drop is 6 volts. Why is that helpful? Well, it's helpful because we know the loop rule exists. The loop rule says you got to get your potentials to work out. So notice that we gained 30 volts when we went up the battery. So we got to drop 30 volts by the time we get back. And notice I have two possible routes I could take. I could go through the 12 ohm or the 24 ohm. Doesn't actually matter which one I take because I have to drop all the way back. So you might find it easier to actually do the subtraction on your circuit. So notice our potential here was 30 volts. Then I drop 6, so that gets me to 24 volts. And notice here, I'm going from 24 volts down to my blue 0 color. So I must have dropped 24. So notice you can actually see that this is encoding the loop rule because I see 6 plus 24 equals 30 on either loop I take. So we unlocked more information. Loop rule told us the voltage drop across the remaining resistors were 24 volts. So we can just do simple division to find our currents. Because delta V is 24 volts, so 24 over 12 means that there's 2 amps through that resistor, the 12 ohm, and there's 1 amp through the 24. And it makes sense that yes, the current splits, right? The current definitely splits from the initial 3 amps. There were 2 amps that went through the 12 and only 1 amp that went through the 24. Makes sense because the 24 would be the slow lane, so it gets less current. All right. Put it off for long enough. Now I'm going to do my mental math. Oh, this isn't bad. 24 times 2, 48. 24 times 1, 24. Does this work out to 90? So this is our last little consistency check, so it should work out. 18 plus 48 plus 24. Well, 18 and 48 makes 66. One off of greatness, I suppose. 66 plus 24. Yeah, that's definitely 90. As expected. So we do see that our power outputs from the resistors add up to be our battery input. So this would be a fully solved combination circuit. We solve for every current, every voltage drop, every power output, and we colored the whole thing. So this is a really nice problem. All right. Not as nice as this one, though. This is actually one of my favorite E&M problems ever. So a circuit contains 3 identical bulbs of resistance R connected to a battery of EMF E, or epsilon, sorry. The switch is initially open. So what we're doing first is we initially have this open circuit, or sorry, this open switch, so we effectively have these 2 bulbs together. But then we flip the switch, causing the circuit to open up this alternate route. So now there's another bulb incorporated. We actually want to know whether the brightness of bulb 2 increases, decreases, or stays the same compared to before I close the switch. So what happens to this bulb brightness when I flip the switch? And this is very non-obvious what happens. So let's actually think about it. So there's actually 2 effects here. You can look at this using a loop rule argument, which is the more elegant one, but less obvious, or you could try to do a junction rule idea. So if we're just looking at what happens here, notice if I flip this switch now, my current through the circuit, when it reaches the junction, instead of all of the current going through bulb 2, like it did before, now some of the current will go through bulb 2, and some of it will split to go to bulb 3. So it looks like there's this effect of the junction rule where you open up another path, so some of the current is being stolen by bulb 3, so the brightness should decrease. But we have to be a bit careful about that argument, because also by adding this extra path, you've decreased the resistance of the circuit, because parallel paths decrease resistance. So actually the battery's pumping out more current. Now you could actually argue that you didn't half the resistance, so the splitting is actually going to reduce the current more than Req increases it. But your first argument and your intuition actually is correct, that this sort of current siphoning effect does actually make the bulb dimmer. So how can we think about this with the loop rule, which involves a little bit less gymnastics? So notice that as I close the switch, what we're doing is we're adding a bulb in parallel. So we add a bulb in parallel. So what does that do? Well, adding a bulb in parallel means that Req is going to go down. Because if you add a resistance in parallel, you get that parallel addition reciprocal rule, which is going to decrease resistance. So what does that mean? Well, if Req decreases, the total current in the circuit is going to increase. Cool. Where does that get us? Well, I said this is actually a loop rule argument. So if the total current in the circuit goes up, who gets hit by that? Well, if we look at our circuit, if the total current goes up, who's getting hit by the total current directly? Well, it's going to be bulb 1. So this means that delta V 1 is going to increase because there's more current. So if you've increased the current through bulb 1, you have increased the potential drop. But you can't just drop more potential across bulb 1 without a compensation across bulb 2 because delta V2 has to decrease by loop rule. And why do we know that? Well, we know that because the two bulbs, 1 and 2, make a loop together. So if you add the two voltage drops from bulb 1 and bulb 2, you have to get to the battery voltage. So if you're dropping more of the volts across bulb 1, you must be dropping less of the volts across bulb 2. So either of those arguments work. Most students actually look at the sort of Kirchhoff junction rule argument of the fact that flipping this switch sort of steals some of the current from bulb 2 and sends it to bulb 3. And you might have just gotten lucky that you missed the fact that the current in the circuit increases as well. It just turns out that the increase doesn't do as much as the splitting does. So this is a really tricky question. When the switch is closed, another loop is open, so the total current in the circuit increases. This increases the total current in the circuit, so bulb 1 receives more current than before. By the loop rule, the voltage across 2 must decrease, meaning it becomes dimmer. Oh yes, and we've implicitly used the fact that power, which is proportional to voltage drop and / or current, is the thing we're looking at here. All right, calculate delta V closed over delta V open for bulb 1. Okay. So let's start with the closed switch. So first we got the closed switch. So for the closed switch, we have the circuit. So we see that Req for this circuit, which we already actually calculated before, is going to be R plus R over 2, which is 3/2 R. So this means I total is equal to the battery EMF divided by Req, which is 2/3 epsilon over R. And again, how did I get that Req? Well, remember, these two are in parallel, and parallel corollary says if you combine identical resistors in parallel, two of them, it halves resistance. So delta V in the closed position for bulb 1 is just going to be IR, which is 2/3 epsilon over R minus times R, which is 2/3 epsilon. That's not what we wanted. We want the ratio of the closed to the open. So we'll send this to the side up here. It's actually a lot easier to do in the open case. So now let's do the open switch. So if the switch is open, the right loop is just cut off. So we just have a very simple series circuit. a very simple series here. So Req is just going to be 2R, which makes our total current the battery EMF divided by 2R, which works out to 1/2 epsilon over R. So this means delta V open is just going to be IR once again, which is 1/2 epsilon over R times R, which is 1/2 epsilon. And this one is more obvious. Like, I don't know if we really needed to work this one out to know that, right? In the open case, it's literally two identical bulbs in series, so they should share the voltage drop equally. But we didn't want that. We wanted this ratio. So delta V in the closed position divided by delta V in the open position is equal to 2/3 epsilon divided by 1/2 epsilon. And now we have the most difficult part. We gotta divide fractions. Keep change flip. 2/3 times 2/1, which is 4/3. So this means the closed voltage drop is 4/3 of the open voltage drop. So is this consistent? Well, we just said that when the switch is closed, there is a higher voltage drop across bulb 1. So yes, it's consistent. Because if there's more voltage drop across the first bulb, there must be less voltage drop across the second bulb, and therefore a lower power dissipated. Right? Ratio is consistent. So since the voltage across bulb 1 increases when the switch is closed, the voltage drop across bulb 2 must decrease. Thus, the power must decrease for bulb 2. And why not? We got to add the as expected. We always say this is how you trick people into knowing what you're talking about. You can say the most random garbage, but as long as we include as expected at the end, we have the divine foresight. Yeah, this is a really hard problem, but this is, like I said, probably it's definitely my favorite circuit problem, because it's both conceptual and mathematical at the same time. I like that you can attack it with voltage or junction rule too. All right, this is not a huge part of physics C, but we at least need to be able to set these up. So there comes a time where the resistors cannot be combined. It looks like, I believe if it's any resistors 4 or less, you can definitely combine them. But as you start adding more, you can get stuff that can't be combined in series or parallel. So the easiest example to look at, or at least to build, that can't be reduced is this object called the Wheatstone bridge. So it's this 5th bridge resistor that makes this irreducible. Because notice, I'm not forced to go through this resistor and a single one. So I have a choice. But also, these two don't form a loop with each other. So there's none of these are actually in series or parallel with each other. So the only way to solve these irreducible circuits is to set up loop and junction equations. But the more common case we'll see in this class is actually multiple batteries. So if you have multiple batteries, you also need to set up loop equations. So if you can't reduce your circuit, what you should do is label all the junction points and label the unique currents. You can just take a guess as to what way the current goes, because if you have competing batteries, it might not be obvious which way the current will go. If you guess wrong, no big deal, you'll just get a negative answer. And if you get a negative answer for current, it means you guessed the arrow wrong. Then we got to do the loop rule and junction rule until you have enough equations. So just like in algebra, if you're solving for x and y, you need 2 equations. You just need as many equations as you have missing currents. Usually you'll accomplish this by having one junction equation and a bunch of loop equations. So let's show this. So here's a case where we have two batteries. So the following circuit contains resistors that cannot be combined, right? This is not series or parallel because I don't have to go from this resistor to this one. I could go through the battery. They also don't make a closed loop with each other because the other battery. So this is not reducible. So we want to draw all three distinct currents. So it seems that there are sort of these two junction points. So notice here, since this is called EMF 1, let's call this I1. And since this is battery 2 or EMF 2, we'll call this I2. So notice that these batteries are going to pump a current. And if they're very unbalanced, of course, one of the batteries could win and just totally dominate the other one. They're both trying to push their currents the way they normally would. So we're just going to assume they do that. Then we see here that I1 would reach this junction point, I2 would reach this junction point, and then they can sort of combine to go down this path to get I3. And if we did the same thing in the bottom, we'd get the same junction equation because we would see that I1 must also be this way to come out of the battery, and I2 must also be this way to come out of the battery. So I3 must be this way. So we get the same idea. So derive two distinct loop equations for the circuit. So by distinct, we mean linearly independent equations or ones that aren't multiples of the other. So first of all, let's do this loop. So let's say I'm going this way. Let's do this loop first. So if I did that loop, first, we would go from negative to positive through our first EMF. Then we would drop some volts across R1, then we'd drop some volts across R2, and then we're back. So I can go through my battery, I can drop some volts across R1, I can drop some volts across R2, and then I'm back. Okay. And again, I'm doing minuses here because I'm going with the current the whole time. So no weird sign shenanigans. And also we can plug in values here. Our first battery voltage was 18 volts. The current through R1 is I1. And R1 is equal to 5 ohms. The current through R2 is I3. And its resistance is 2 ohms. So that would be a loop equation. So we will box that one. And then we want another loop equation. So if you want to get a really weird loop, you could actually do this outer one and you'd have to go backwards through one of the batteries, but that's a bit annoying to manage the signs. So let's just pick this one. Let's just pick like the smaller loop because we only go through one resistor. So this one actually becomes pretty simple because notice I will go up through the battery and then I'll drop some volts through R2. So my second loop equation will just look like gaining some volts across the second battery, then I drop those volts across R2, and then I'm back. Our second battery voltage was 8 volts. Current through R2 is still I3. Resistance of that is still 2. All right. Not enough yet, right? I have 3 currents I would like, and I only have 2 equations. So what's a junction equation? Well, the junction equation is always the easiest one. It's just ins equals outs. So we know that the sum of the currents in equals the sum of the currents out. My currents in are I1 and I2, and my current out is I3. All All right, so this is actually a fully solvable linear system. So by combining our loop and junction equations, calculate all currents. So this is about the extent you'd have to do in Physics C, by the way. We're usually not going to make you solve these. It's usually about setting up weird loop equations. That's about it, but let's solve it. This is not terrible. In higher level, you just shove this into a matrix. All right, our first equation said 18 minus 5i1 minus 2i3 equals 0. Our second equation said 8 minus 2i3 is equal to 0. And our third equation said i1 plus i2 equals i3. Now, no weird system tricks are needed here. We can literally just see that there's only one current in this middle equation. So since 8 minus 2i3 is equal to 0, this means 2i3 is equal to 8. So i3 is equal to 4 amps. So we've unlocked one of the three currents. And now, as we do with any linear system, once you solve for one of the variables, you just start plugging back in. So now our top equation says 18 minus 5i1 minus 2 times i3, which is now 4, is equal to 0. So 18 minus 5i1 minus 8 is equal to 0. What is 18 minus 8? That's 10. So 10 minus 5i1 is equal to 0. So 10 is equal to 5 times I1. So I1 is equal to 2 amps. That's a second current unlocked. Let's box this for consistency. All right, third equation. Well, we have one equation left. I1 plus I2 equals I3. So we have I1 plus I2 is equal to I3. I1 is 2 amps. I2, we don't know. And I3 was 4 amps. So I2 is also 2 amps. So now we can go ahead and just write everything down and solve for everything and make sure our loop rules work. All right, so we said that I1, which was defined as the current that came out of battery 1, I1 was 2 amps. The current that came out of battery 2, I2, was also 2 amps. And the current that went down the middle branch was 4 amps. That is what our system solved for. Now it wants us to calculate voltage drops. Well, delta V is IR. So IR, well, I is 2, R is 5, 10 volts dropped here. Delta V is IR. I is 4, R is 2, voltage drop is 8 volts here. And now, if we actually color our potential for this circuit, this would be, so we know that since there's no resistances down here, we can actually define ground to be right here. We could say this is 0 volts. So I call this the red because this is being stepped up by 18 volts. So 0 step up to 18 would be 18 volts. Then here we're at 0 volts stepping up 8. So this is a kind of funky potential diagram. Would get me to 8 volts and so on. So actually notice all our loop rule checks work, right? I have 18 volts here. I drop 10 across this resistor, 8 across this one. Same thing here. I have 8 volts that I'm stepped up here, and I drop all 8 volts across this resistor. And also notice all the potentials work out. 18 volts minus 10 volts gets me to 8. So all our potentials match forwards and backwards. So even in the combination circuit with multiple batteries, we can still analyze it this way. This is a nice little problem, not usually expected to be seen in Physics C very often. We're more concerned with the setup than doing this. But something like this could be a fringe multiple choice item if we wanted a really hard one. All right, that's Unit 1. Everything with circuits that don't involve capacitors.